started? Good morning. It's nice to see so many of you back again. I'm sure if I need more people here, we can pull the fire alarm and it'll fill back up. So what we're going to do this morning is, let's see where we started last time. We started last time with the atom kind of at the top of the chart here. The most straightforward thing that we're talking about in terms of how much you interact with them in daily life and what happens and what your daily experience is. We got through a lot of the work last week of what are the parts and how do they work together and this sort of thing. What we didn't manage to get to last week was a lot of the information on examples of how you see this in everyday life and what happens and how it actually affects you. So we're going to start out with that, still staying with atomic physics for the first half hour or so this morning. And then we're going to move on to nuclear physics. Nuclear physics is what I did my PhD work in, so it's got a special meaning to me. It's still in the realm of stuff that affects our technology and things that we hear about on the news and stuff you kind of need to know about. It also answers those questions of where we all came from, what we're made out of, what the Earth is made out of, a little bit of how the universe came to be that way. I'm not going to spend a lot of time talking about cosmology here. We'll talk about supernovas and stars and the sun for a little bit. That's not really the main subject. Those are really examples of why nuclear physics is important. And that will also bring us into fission and fusion, things like atomic power and atomic bombs. So that's the goal for today, is to kind of get that far and understand that and see where atomic physics and nuclear physics are similar and where they're kind of different. You'll see as we go through, there's certain themes and analogies that you can draw between each of these different realms here. How straightforward they are, how intuitive they are, changes a little bit, and how accurate our casual descriptions of them are changes a little bit as we get deeper. But a lot of the same themes come up over and over again, which is part of why I have it organized in this way. So where we left off last time, I'll just say a couple words of what we need to know to refresh our memory before we go on here. We have the atom. The atom has a nucleus. Let's see, I'll start on this board. And the nucleus has, it's made up of stuff, which we'll talk about later, protons and neutrons. It's a ball of things inside here. And then around the nucleus are the electrons. And we talked about the electrons that have the negative charge and how they circle around and around. They don't actually circle around and around. They're in a cloud, they're in kind of bubbles in different places. But the Bohr model of the atom, that's what Niels Bohr won the Nobel Prize for, worked on the assumption that they do go in essentially these rings or these shells that are concentric circles around the nucleus. The nucleus is positive. The electrons are negative. That plus and minus charges attract each other. But we have a rule here that says that you remember the electrons, like all particles, are particles and waves. So they wiggle. And again, this is something that is not actually true, but we're going to think of it this way, and it'll give us the right intuition. The particles kind of wiggle around like that, with a certain wavelength. The wavelength is how far apart the peaks of the wiggle are. And what that wavelength depends on is how big the particle is, how massive it is. Not big in terms of size, but big in terms of mass, which again, mass and energy are the same thing, they're totally interchangeable. So it's how much energy it has or how much mass it has is that wavelength, is the size of those wiggles. And the Nobel Prize idea for the Bohr model of the atom is that these electrons, as they go around the nucleus here in the atom, these electrons have to wiggle an integral number of times, once, twice, 3 times. They can't do 2.5 times or 2.25 times. And that's why, even though you have a positive nucleus and a negative electron here, and they want to attract, why don't they come in and crash into each other? Why don't they come to form one thing? Because you have to have at least one wiggle as you go around the circle. And I can't have less than that. It's one of these sort of absolute rules of quantum mechanics. And that means that I can't get any closer. But I can get further away. And I get further away by adding more wiggles. So if I have one wiggle, it'll be that first shell. If I have 2 wiggles, then maybe I'm in that second shell. So wiggles once here and one wiggle there, and they match up. And that's essentially what these pictures are. I've got 3 here, 4, 5, 6, and again, each of these then gets bigger because it's got to fit those wavelengths in. It's got to fit the wave in. Now, wavelength is the same. The wavelength is not going to change. That depends just on the mass of the electron. So if I have the same wavelength and putting more waves in, I have to make the ring bigger to fit them all in. And that's what happens. That's the model of the atom there. Now, what's important for what we're talking about today is that to do that, to make this next ring, okay, so I'm coming out here now. For my electron to go from here to here, I'm getting further away from the nucleus. And if I'm getting further away, I need energy to get it out there. Barbara?
That was sort of my question. So the electrons that are further out actually have more energy than the electrons that are closer in? Or they have more mass?
An atom with an electron further out has more energy than an atom with the electron closer in. The electron itself has basically the same amount of energy. But there's energy in the atom as a whole, and I have to add energy to the atom to move the electron out. And if the electron moves back, I have extra energy left over.
Well, the outer shells, the wavelength is longer.
The wavelength is the same, but I have more waves in the shell.
Yes. All right. And in order to do that, those electrons have more energy?
The atom has more energy. So we'll see that. That's really the subject of what we're talking about this morning, so we'll get to that. So that's basically the thing. I've got my positive nucleus, I've got my negative electron. They want to come together. They're as close as they can get when I start out, because I can't have less than one wave in there, and then one wavelength. And if I add energy to the atom, I've got an atom, and somehow I put energy into it, where does that energy go? That energy pushes the electron out into the next shell, out into the next orbit. But the distance between these two has to be by an integral number of wavelengths. I can't add any amount of energy and move any distance out. I can only move into the next shell, or the next shell, or the next shell. There are fixed spacings between them. It's not the same space between each shell, but there are fixed spaces between them. And what that space is just depends on which atom it is, how many protons I have in the nucleus, because that determines how tight this attraction is.
I think I may have asked you this the last time, but help me out anyway.
Sure.
With the additional shells, the electrons are negative.
Right.
The nucleus is positive.
Right.
Why are the various shells not repelling one another?
They do, but what happens is this is not just +1 in the nucleus in general. If I have multiple electrons, this could be, there could be 5 protons in here. So then it would be +5. And then I'm allowed to have 5 electrons, they'll all still stick. And there's something called screening, which is if I have an electron in here, if this is +5, and I have one electron here, this one doesn't see an attraction of +5, it sees an attraction of +4. Because anything that's inside gets averaged together, essentially. It's all added together, and from outside I don't see anything. That's why when atoms normally are neutral. When you see them as neutral, you're not attracted to them, you're not attracted to the nucleus inside, because that ring of electrons on the outside, what you see is the overall average, the sum of the entire thing.
So in a way that's what allows that electron to be further away, because it sees the charge actually as less of a draw?
No, it's further away just because you've added energy. Now, what I'll say, what we're talking about this morning, to start out with, to keep it simple, is I have, regardless of what I have inside the nucleus here and how many charges, I'm going to talk about an atom that has 1 electron. And that 1 electron is moving out or moving back. Nothing really changes except what the energy levels are if I start adding more electrons to the picture. It just gets a little more complicated, but it's the same basic story.
I can see the balance in terms of charge by adding each proton, but in terms of mass,
right.
The neutron is almost the same mass as a proton is.
Right.
So how is this balanced?
Mass doesn't come into atomic physics really at all.
No, but it does through the Einstein's equation.
There's no interaction there at all. The mass, well, we're talking about atomic physics is really just an electromagnetic story. There's no other, the other forces don't come into atomic physics really at all. So gravity, nothing Einstein did applies. None of relativity applies. Einstein photoelectric effect, which is what he got the Nobel Prize for, is part of our story here. So I can draw energy levels. If I'm in the lowest possible orbit, I'm as close as I can get, as close as I'm allowed to get. That's 0. That's the lowest energy I can have. I can't get any energy out of this by moving the electron around. But I can be in this next shell, and then I would be at the first energy level. And then maybe I can be in the shell after that, and there's another energy level. And I can go higher and higher, and I can keep getting more and more energy levels. Now you can imagine, as I add these, the difference between 1 and 2 and 2 and 3 is kind of big. By the time I've got 50 waves or 51 waves, that's not a big difference, relatively speaking. So what happens is, as I add energy, I go to these higher shells, they get closer and closer and closer together. Until I get to a point where I've added so much energy that the energy I've added is more than the attraction between the electron and the nucleus, and then the electron is free to go. And that's how it's ionizing. This is the word that would be used, because it means I'm taking the electron and I have escaped the nucleus entirely. And so my atom now has one less electron than it used to. So there is this amount of energy I can add that's enough that the electron is free. And then I'm just left with the nucleus and no electron if I started with 1. So those are my energy levels, and the way we talk about these is with transitions. I can make a transition from one energy level to another. I can start in 0, this is called the ground state, that's where I cannot get any more energy out. And if I go up, I can go up to the first excited state. Okay? So to do that, I need to add energy. The way typically energy is going to be added is by a photon coming through. Remember, photon is the particle of light. Light waves, is light particles, the energy. Photons can be any kind of energy, any amount of energy. And what determines the energy of a photon is just its wavelength, which you think of as the color of light. What the frequency of the light is, what its wavelength is, its color. Those are all equivalent statements. So a photon comes in, like this. Photon we write as gamma. And that photon if that photon has this much energy, then it will push the electron from the ground state to the first excited state, from the first shell up to the second shell. If that photon has more energy, it can get it up to the second state, or the third state or the fourth state. If it has enough energy, it could free the electron entirely. If I have an electron that's sitting in one of these outer shells, in an excited state, one of the overall themes of physics is that everything wants to get rid of whatever energy it has. Energy is like a pressure that makes you want to get rid of it so you can get down to some ground state in any branch of physics anywhere. And most of what physics is here, and all of this stuff, is what the rules are that keep you from getting down there, because you're going to take whatever path you can. So if I'm in an excited state and I'm allowed to go down to a lower state, that will happen. And it's the same picture, I just change the direction of these arrows. If I'm in the first excited state, I'm in the outer shell, and there's nothing keeping me from going down to the first shell, it's not already occupied, I'll fall down to the first shell, and I'm going to give off a photon, and that photon will have the energy of that state transition. Okay. That's the decay. It's radiation in a sense. Any kind of energy coming off anything is radiation of whatever form. So we have the excitation, and we have the decay, which is what we call those things. I add energy, I get excitation, I decay, and then the energy comes out. And there's a certain amount of time, if I'm excited, if I'm in this excited state, I'm in one of these higher shells, and I have this pressure, I want to get down to the ground state. There's a question of how long it's going to take to do that. How long do I have to wait? How much pressure is there? And that depends on a number of things. The most important thing it depends on is how much energy there is. If I'm standing on the edge of this cliff between the first state and the ground state, and I can go down there, and it's a big drop, I can get a lot of energy out. I'm going to get there much faster because it's like there's more energy pressure. These are not technical words here, but it's more energy pressure kind of pushing you down. You'll decay much faster. If there's a smaller space between those states, and I can't get as much energy out, there's not as much pressure, because I'm not in that much of a hurry to get down there. So the lifetime, or the half-life, would be higher, would be longer. It takes longer for me to drop from one state to the other. Now, these are statistical processes. When I say it takes 2 seconds, or the lifetime is 2 seconds, it doesn't mean I wait till 2 seconds ticks and then I drop down. That means on average it's going to be 2 seconds. Sometimes it's a little faster, sometimes it can be longer, but if I have 100 million of these things all sitting next to each other, the average that average lifetime would be 2 seconds in that case, if it's got a 2-second lifetime. It depends mostly on the energy. The other thing it depends on is how many ways I can get there. In this simple picture, there's one way up, there's one way down. There's one place to go. So it's fairly straightforward. But if I have a place where there are multiple states in some of these things, I have multiple ways to get there, multiple paths, then I have lots of choices, it's going to be faster. Because it's essentially, I can take this path, that would take 2 seconds, this path would take 2 seconds, so it will only take me 1.4 seconds if I can go either way. Because I have 2 different options, and the clocks run in parallel in that sense. So those are the things that affect the lifetime of the atom. So what we have, photon is not the only way that I can add energy. These things are flying around, and if they collide or something comes in and punches them, I can add energy that way. I can have, so one way this is used is in the street lights, the sodium vapor lights. These yellow street lights, most of them are yellow, especially the older ones are all yellow. They're yellow for a specific reason. What they're filled with is sodium vapor, sodium gas. So these sodium gas, sodium atoms that are flying around, and these atoms are just flying around everywhere. It's a gas, they're all just kind of wherever they are. And the way the light works is it has a coil here that spits off electrons. And those electrons just go flying, it shoots them out. The way it does that is there's an electric field that it generates, so the electrons are being pulled across. These are just free electrons. It turns out it's possible if I have a wire or certain other materials, if I get it hot enough, there's different ways to just start spraying electrons at it. It's the same as this, where I have to give the electron enough energy to get free of the atom, and I can do that with heat or with electricity. There's other ways to do it. But in this case, what's important is that I have these electrons, they're flying around through this thing, and I have these sodium atoms. When the electron hits the sodium atom, the energy from that electron is going to hit one of the electrons in here and bring it up to a higher orbit, a higher level, higher energy level. And it's going to sit there for a little while. And then it's going to fall back down. And when it falls back down, the photon comes off. So the electrons that are coming in it's a mess of energy. It's all over the place. They're just kind of random photons being sprayed out. Random electrons being sprayed out. When they hit the atoms, they add energy to the atoms if they can. And then when those atoms decay, when the electron drops down to the next lower shell, it gives off a certain amount of energy. But remember, these shells are a certain spacing apart. They're always the same spacing apart. It turns out that in sodium, there are 2 transitions that are right near each other. This one, let's say these 2, this one and this one, sorry. These 2, so I get 2 different kinds of photons that come out. 2 different energies, very slightly different. And those energies correspond to yellow light, yellow-orange light. And that's why all the light that comes out of sodium vapor light is that yellow-orange color. It's really 2 different colors that are mixed together. The 2 colors are very close together. But it's unlike sunlight, which is a broad spectrum where you can see a rainbow. If you have a little prism up to a sodium vapor light, to one of those outdoor street lights, you won't see a rainbow. You'll see 2 lines in yellow right kind of next to each other. And it's because you can only be in these lab states. There's only certain orbits you can be in. And that restriction to those certain orbits means you can only get photons of a certain color. You can only get that color out of those lights. That's why the street lights are always yellow like that. What we had is 2 Nobel Prizes I just want to hit quickly before we move on. They're kind of relevant to all this. To help us figure out that this is what's actually happening. The first is the photoelectric effect. So if I have an atom with my electrons, I've got my nucleus in there, I have my electrons going around the outside. If I hit it with a photon, I shoot a photon into this, I can spit out the electron. I can get this guy to go flying out. Knock him away from the atom. But not just any photon. That photon has to have a certain amount of energy. It has to be above a certain threshold. If the photon is is not energetic enough, it won't happen. That's the first thing. The second thing is that, so that was the first experimental piece. The second piece was that what matters is just that, the color of the light, how much energy that photon has. It doesn't matter how many photons I have. There's no, it can be a very dim light, and it will still, if it's above a certain energy per photon, if it's a certain color, the electrons will come off. But if it's a very, very bright light, incredibly intense, but it's at a color that's below a certain energy, then I need to get this electron out. No electrons come off. That's called the photoelectric effect. Photo is light, and the electric means the electrons come out. I see the electrons come out because I get electricity flowing somewhere. And that's what Einstein got the Nobel Prize for. Who? Einstein. Because what's happening here, figured out, is that that amount of energy corresponds to the distance from that outermost shell all the way to the ground state. So if I'm sitting here and I have enough energy to get past this, then the electron goes free. And if I have any amount of energy that's less, anywhere else in here, it doesn't go free, no matter how many photons I have. And that's what you think of as the brightness of the light or the intensity of the light. I can have a really, really intense light. If all the photons are only this big, that much energy, then the electron is not going to come free. So it's the wavelength, it's the color of the light, it's not the intensity. And that's what that Nobel Prize was for.
Going back when we are bombarding it with electrons,
Yes?
why is it that the atom itself becomes unstable? Do I have, when I'm bombarded with electrons, I have to fill the second shell?
No, the electrons are just billiard balls. They're just coming in with energy, and they hit, and now if I absorb that, then I've added energy somehow.
But what makes them collapse to a lower level?
If they're allowed to, they will. I will always give off energy, I will always collapse to a lower level if I have any way to get there. The only way I won't do that is if there's some rule that prohibits me from going to the lower level.
But lower level means that somehow I am losing energy
Yes.
from the shell which I have been in.
I'm moving to a different shell. That's how you give off the energy. I move to a lower shell, and the energy comes off.
But somehow I managed to sustain myself for a while in the higher shell.
Right.
So what made me, is it a random event?
It is a random event, and the amount of time it takes depends on mostly how much energy I would get back, how much energy I would give off. If I'm only going to get a little bit of energy back by moving to a lower shell, I'm not in such a hurry. If I'm going to get a huge amount of energy back, then I'm in a real hurry. I want to get down there as fast as possible. But otherwise, it's a random event. The amount of time is probabilistic. So okay, we'll do a couple quick questions and then move on.
Two things I intend to relate. You simplified only describing mostly one transition.
Right.
On the right. I'm assuming that things could transit between whatever shells are currently occupied by, especially if it's an electron, if it's an atom that has lots of electrons,
Yeah.
that has lots of things going on, then things can go, there are all kinds of different steps that could be made.
There are all kinds of different steps, but there tend not to be things that happen simultaneously because one electron comes in at a time, one photon comes in at a time and hits the thing, and then there'll be this transition. And it's really from one thing to another thing. I'm not going to have one photon come in and then two electrons go this way and one go that way.
Well, that's the next thing. But if there's just lots of random energy around, you take something and you put it over a fire, and you're adding heat to it.
Right.
Or you take it, you put it out in the sun, so you're adding all the colors of light to it.
There are lots of atoms and they're very small. So these things still will happen one at a time.
So it's a question of how tightly you narrow your focus.
Even when you have a very intense light or you're adding what you think of as a lot of heat or a lot of energy, it's not that much per atom. There's so many atoms that you don't have a lot of photons coming in. You don't have a lot of stuff coming in. There are cases where we'll talk in a minute about lasers where we try to get as much of that going as possible. But if one electron comes in, it's sort of like fertilization of the egg. Once one comes in and the photons moved up, or the electrons moved up, it's in a different state. So now I need, if another one happens to be the right energy to move, it'll do it again. So the next prize, the next Nobel Prize I want to talk about is similar to the photoelectric effect. This is Frank and Hertz that did this. And in this case, what they're doing is instead of having a photon come in and seeing what happens, they have an electron comes in and they see what happens. In this case, the electron comes in, and it comes in with a lot of energy. It comes in and bounces off. Now, there's an important difference here. between the photoelectric effect, where I had a photon, and the photon has to be the right energy to get absorbed. The photon's got to be this much energy. So I can't just give some and keep going. And an electron comes in, it can hit and bounce off and give some of its energy. It doesn't have to be exactly the right amount of energy. So in this case, I have an electron come in with a certain amount of energy, and then I have that same electron kind of goes through, and this is, we don't know what's happening here, at least when we get the Nobel Prize, we know before we do it. There's energy that comes off here, and this energy is less than the first energy. Right, so this is the energy, E1 is the energy that it comes in with, and then it loses some energy when I detect it on the other side. So it turns out that they measure this, and they measure this, and they measure this, and it always lost the same amount of energy. It always lost 4.9 electron volts. Every time they do it, 4.9 electron volts comes off. It's always lost. It doesn't matter what energy I'm coming in with. I always have 4.9 electron volts less than I had when I came in for these electrons. And then it turns out that I happen to see a photon come off. And that photon comes off at an energy of 4.9 electron volts.
Yeah.
This is the thing that Einstein said, it's a result so beautiful it makes you cry. Now you see here, because we went through this already, which they didn't have, what happened? The electron came in,
What was the name of the person who won this Nobel Prize?
Frank and Hertz, two guys. Frank was the Jewish one. Hertz was not. You see, now we have this picture, what's happening? My electron comes in, I'm sitting here in the ground state, it gives me enough energy to get here. This is 4.9 electron volts, it's the distance from here to here in the particular atoms that we're working with. So my electron comes in, it leaves behind a certain amount of energy, and it goes off again. A minute later, the atom decays, the electron goes back from this shell to this shell. Again, this is a 4.9 electron volt difference. It got pushed up to here, it comes back to here, and shoots off that photon. And that matching of everything up, that was a Nobel Prize worthy result there. Okay. So now that we have these pictures, now we can understand something. Talk briefly about the sodium vapor lights, but there's a couple other things that we see, or that we use, that
John,
now understand. Yeah.
here, when the photon comes in and the electron gets excited and then it drops back down, is it the same amount of energy that comes off as went in?
In that simple case, yes.
Yeah.
And so what the simple case is, this is actually an important point. The simple case here, where it just comes up and comes back down again, that's what you see. That's what color is. So I'm sitting here and the lights are coming in and they hit my shirt and what you think of is light comes and it reflects off. Light's not so much reflecting off. The light's getting absorbed and immediately re-emitted at the same color. Just going back and forth. So the photon that comes in is not the same photon that comes out. It's a different photon. The photon got absorbed and it gets re-emitted. And that's what certain things are certain colors because of that. You're seeing the colors of the photons that are coming out from those transitions.
You're focusing on just the yellow. You're talking about traffic light, right?
No, sodium vapor lights, the street lights.
Oh, the street lights.
The floodlights, the regular street lights.
Oh.
Okay, so what this gives us now is a slightly more complicated case. I have the ground state. Now I have, let's say just for simplicity, I have two states. I can get the photon in, and it comes up to this state. It can come down to that state. And I have one color of light go in and a different color of light come out. This is fluorescence. So if I have a black light, fluorescent light, UV light, that's where blue is the higher energy photons. UV is the higher energy photons. So here I have a high energy photon come in, and then I have a lower energy photon come out. The color of light that comes out is different than the color of light that came in. And that's what fluorescence is. We have anything that glows in a black light like that, that's what's happening. So that's fluorescent light bulbs. That's how they work. A fluorescent light bulb is kind of like the sodium vapor light that I talked about before, where you had just those two yellow lines because the electrons came in and excited it.